Okay, welcome back, sports fans. Mr. Noldy here. Today, I was just going to show you a quick example of how to use the second derivative to classify critical values or critical points if you have those. So, a couple of things to remember is that when you have a function and you take the second derivative has a couple things that it tells us. First off, if the second derivative, is less than 0, that tells me that I'm looking at something that's concave down. So up here, we would be classifying a relative max. I'll just abbreviate that. The second thing about the second derivative is that if I have a second derivative greater than 0, that means I'm looking at a region of the curve that is concave up and therefore represents a relative minimum. And last but not least, when we get to inflection points, when the second derivative is equal to 0, you have identified an inflection point. So an inflection point, remember, is just one side of the curve, something like this. So this would be an inflection point. It's concave down to the left and concave up to the right. So it's concave down on the left and concave up on the right. So this is what happens when we find a second derivative that is equal to 0. We have identified an inflection point. So let's look at an example. Okay, so here is a function. P of t is equal to negative 3t to the fifth, that's a 5. I could have made that look more gooder, plus 5t cubed. So what we want to do here is classify our critical values. So the first thing we need to do is find the critical values. So that means take the first derivative. So p prime of t is going to be negative 15t to the fourth plus 15t squared. So in order to find the first derivative, we would set this equal to 0 and solve for t. So I would say, all right, I have a negative 15t cubed, I see. No, t squared, common to both of these factors. 15t squared in here, and there's a 15t squared in here. So if I take that out, I end up with t squared. And let's see, if we take 15t squared out of there, negative 15t, that's just a minus 1. So remember, one way to double check, this is going back to algebra, but negative 15t squared times t squared is negative 15t to the fourth, and negative 15t times negative 1 is positive 15t squared. So remember, this is all equal to 0. So that tells me that t equals 0 over here. And let's see, this would keep on factoring here. So before I write that, let me go ahead and undo, let me keep on factoring. Negative 15t squared times t plus 1 and t minus 1. Because remember, when you have a difference of two perfect squares like this, it factors into the product of the sum and difference of two numbers, and those two numbers are the square roots of t and the square root of 1. So if this times this equals 0, either this is 0, or this is 0. So here we go. Negative 15t squared equals 0, or t plus 1 equals 0, or t minus 1 equals 0. So when I divide both sides by negative 15, I get t squared equals 0, or t is 15 because 0 squared is 0. I'm sorry, t is 0 because 0 squared, when I square 0, I get 0, so the t is 0. In the second one, let's see, I have t equal to negative 1. And in the third factor over here, I have t is equal to positive 1. So these are my critical values. So those are what we're looking to classify, right? Critical values. Let me write this down. Critical values. All right. So the way we classify these is we have to take the second derivative. So I'm going to look at my first derivative here. I'm going to take the second derivative of that. So taking the second derivative, I end up with, let's see, p double prime of t is going to be equal to negative 60t cubed plus, was it 30t? Yes, 30t. So I'm not going to set this equal to 0 unless I want to find an inflection point, which we talked about in the previous slide. What I'm going to do is just substitute critical values in here. So p double prime of 0 would be negative 60 times 0 cubed plus 30 times 0. So that equals 0. So what this tells me is I've identified excuse me, an inflection point. So, or a critical value of an inflection point. Then if I did what is t double prime of negative 1, well, let's see, we have negative 60 times negative 1 cubed plus 30 times negative 1. So let me see, this becomes a negative 1 times negative 60, which is 60. Negative 1 times 30 is 30. So 60 minus 30, that ends up giving us a positive 30. It's not really important to find out exactly what this 30 is. It's just that it's positive. So that tells me that I'm concave up. So at p equals negative 1, I have identified a relative minimum. I'll write that in there. And last but not least, p of positive 1. So that's just negative 60 times 1 cubed plus 30 times 1. So now we're looking at a negative 60 here plus 30. So that's a negative 30. But the important thing is that it is negative. It's a negative 30. So that means this region of the curve, whatever curve this is represented by, is going to have a concave down. And so that means that at p equals 1, we're looking at a relative maximum. So that essentially is it. That's identifying relative mins and maxes, or classifying them as relative min or max, or an inflection point, using the second derivative. Now, if I wanted to, I could go back in and find those points. So let's do that in the next step. All right, so going back up to the this function here, we're going to figure out what the actual points are. So negative 3 times 0 to the 5th plus 5 times 0 cubed. So that's 0 plus 0. So 0, 0 is an inflection point. Let me write that. That's good enough. And then we're going to have negative 3 times negative 1 to the 5th power plus 5 times 1 cubed equals. So that's going to give me what, a 3 minus 5, or negative 2. So that means that negative 1, negative 2 ends up being a relative min. That point, this is a critical point. These are critical values over here. So last one, p of 1 ends up being 3 times 1 to the 5th plus 5 times, whoops, this would have been a negative 1, wouldn't it have been? That would give me 3 minus 5, oh, negative 2. All right, that worked out by happenstance. So 1. So let's see, 3 times 1 plus 5 times 1. That's 3 plus 5 is, oops, this is a negative, right? Yes, we got that negative. That's important. I remembered it here and here, but forgot it here at first. So anyway, negative 3 right here plus 5 is positive 2. So that tells me that the point 1, 2 is a relative maximum. So we have our relative min, our relative max, and our inflection points identified here. Now, next, let's consider what the graph of this might look like. Before I make my graph, I just noticed this is a negative 2 here, so I forgot to write the negative there. So let me go ahead and do that, and then we'll go to the next slide and show you what the graph looks like. All right, here's a quick sketch I just did. I checked it on my graphing calculator, also on Desmos, and what you'll notice is it comes from upstage left here, comes down, bottoms out at 1, negative 2. So this is one of the critical points. So 1, negative 2. The critical value is negative 1. The critical point is 1, negative 2. Then we come up here. We have a relative minimum, right? It's concave up, and it comes up to an inflection point right here, and it's concave down to the left, concave up to the right, and then it goes up above the 1, so it's at 1, 2. So the critical value is positive 1. The critical point would be 1, 2, and that's a relative maximum. So your minimum, your maximum, and this, let me switch colors here. Yeah, that's more gooder. This is a inflection point, an inflection point, an inflection point. And we had previously determined that this occurred at 0, 0. So there you have it. So hopefully you got some value out of this. If you did, consider sharing it with a classmate. And just don't forget, math's not a spectator sport. I always like to finish these with that. It's not a spectator sport. The only way to learn math is to do math. So until the next time, this is Mr. Noldy signing out.